Let's take a look at these acid-base questions. Question 7.1. The pH of a solution X is measured before and after adding 10 drops of concentrated sodium hydroxide to it. Question 7.1.2. What happens to the concentration of the hydronium ions in solution X? Does it increase, decrease, or remain the same? And the question is telling us to explain the answer by referring to the ionization constant of water. Now, the ionization constant of water, Kw, is equal to the concentration of H3O plus multiplied by the concentration of OH minus. Now, since this is a constant, the concentration of H3O plus is going to be inversely proportional to the concentration of OH minus. As the NaOH drops are being added, the concentration of OH minus is going to increase. That must mean that the concentration of H3O plus is going to decrease. Question 7.1.3 says calculate the concentration of the OH minus ions in the final solution. Now, in the final solution, the pH is 12. So pH plus POH is equal to 14. That means POH is equal to 14 minus 12, which is 2. Now, POH is equal to minus log of the concentration of OH minus. So 2 is equal to minus log the concentration of OH minus. The concentration of OH minus is therefore equal to 10 to the power minus 2, which is 0.01 moles per dm cubed. Question 7.2. A learner titrates a sodium hydroxide solution with a standard hydrochloric acid solution of concentration 0.0958 moles per dm cubed. We've been given the reaction and they tell us that the learner uses a pipette to transfer 20 cm cubed of sodium hydroxide into a conical flask and adds indicator. The solution is titrated with hydrochloric acid and the endpoint is reached. The titration is repeated 3 times. A table of the learner's results is as follows. First question that they ask us, 7.2.1, is to calculate the average volume of hydrochloric acid added. So to calculate the average volume, it's simple. We simply just add up all of these values. And in doing so, we get 60.3. So the average volume is going to be 60.3 divided by 3. And that's equal to 20.1 cm cubed. Question 7.2.2 says, prove with a calculation that the initial concentration of the sodium hydroxide solution was 0.0963 moles per dm cubed. Because this is a titration, we can use the formula CAVA divided by CBVB is equal to NA over NB. This is an extremely useful formula, especially when you have a titration. Now, let's look at the information that we know. Well, the concentration of the acid is given to us, 0.0958. The volume of the acid is what we just calculated, 20.1 being the average, divided by CB, which is what we want. The volume of the base, they tell us, is 20 cm cubed, and Na over Nb is from the reaction. It is the coefficients, 1 to 1. So it's 1 over 1. We can now calculate Cb, and Cb is equal to 0.0963 moles per dm cubed. Now, the standard solution, or the standard sodium hydroxide rather, is used to determine the percentage by mass phosphoric acid in a commercial brand of rust remover. A 10-gram sample of the rust remover is weighed off and transferred to a volumetric flask. Thereafter, the flask is filled with distilled water up to 250 cm cubed. 10 cm cubed of this diluted solution of the rust remover is titrated with 24.45 cm cubed of the sodium hydroxide solution. The balanced chemical reaction is as follows. 7.2.3, calculate the percentage by mass of phosphoric acid in the original undiluted rust remover. Now, Just to visualize what's going on, we have 250 cm cubed and we are adding in 10 grams of rust remover. Now we are going to have some solution here. Now 10 cm cubed is removed and it is neutralized, or it is titrated with NaOH, the volume being 10 cm cubed, and it's the same NaOH as before, so the concentration is equal to 0.0963 moles per dm cubed. And they want us to work out from this 10 grams of rust remover how much of it was actually acid. So what we need to do is we need to work backward. So we'll start here and then we'll work our way there. Now because this part here is a titration, we can use the titration formula. So number one, or part one, I'm going to use CAVA over CBVB is equal to Na over Nb. The concentration of the acid is what we don't know, so leave that as Ca. The volume of the acid is 10 divided by the concentration of the base, 0.0963. The volume of the base is 10, and that's equal to Na over Nb, the reaction here. Acid is 1, base is 3, so 1 over 3. The concentration of the acid is therefore equal to 0.078 moles per dm cubed. And this is the concentration of the acid in the 10 cm cubed. So once we have that, we can then move on to step 2. Now the important bit to understand is that the concentration in the first part, so in this 10 cm cubed, is going to be the same as the concentration in the second part. And the reason is because we have simply removed some solution and poured it into another container. I like to use the analogy that if you are making some cordial or passion fruit or some drink of that sort where you have to mix certain things together, when you make a big pitcher or a big jug of it, say 2 liters of it, and you taste that, that is the equivalent of the concentration. It tastes fine. Then from there you can then pour it out into other glasses. The taste isn't going to change. The taste stays the same. So the concentration likewise will remain the same. So the concentration in the 10 cm cubed is going to be the same concentration in the 250. Now since we know that, we can then calculate the actual mass of the acid in the 250. So we can use the formula. So this is now part 2. Concentration is equal to mass divided by molar mass times volume. The acid has a concentration of 0.078. The mass is what we want. The molar mass of this acid is 98. And the volume is 250 cm cubed, so 0.25. The mass is thus equal to 1.911 grams of acid. Now they want the percentage of acid to the rust remover. So we're going to say that the percentage, step 3, is going to be 1.911 divided by 10, because that's the original mass of the rust, times 100. And that's going to give us 19.11%. Let's take a look at question 8, the electrochemistry question. A learner was asked to build a functioning galvanic cell. The following are provided. They give us a list of items and they then tell us a partially labeled galvanic cell built by the learner is shown below. If electrons move from the left electrode to the right, label the parts 1 to 4 using the information provided. So electrons are moving this way. That must mean that this is the anode and this is the cathode. Now we need to take a look at our rods. We have a magnesium rod and a copper rod. Which one is going to be at the anode and which one is going to be at the cathode? Well, the anode is going to be the one that's going to be oxidized. Remember, an-ox, so oxidized. And at the cathode, we're going to have reduced. So let's look for magnesium and copper in our table. So magnesium, here we go. Here's magnesium. And copper, here's copper. So since magnesium is higher up, magnesium is going to be oxidized. And since copper is lower down, copper is going to be reduced. So that must mean that this is going to be my magnesium rod. That's going to be my copper rod. Now the electrolyte must be something that is related to the electrode that's in it. So for example, 3 cannot be copper sulfate. It has to be magnesium sulfate. And likewise, the copper must be in a solution of copper sulfate. Let's take a look at question 8.2. Write down the equation for the half reaction taking place at the cathode. Now at the cathode, we are going to have reduction, and reduction is written from left to right. So the answer here is going to be Cu2 plus 2 electrons, giving us Cu. Question 8.3, calculate the initial EMF of the cell under standard conditions. EMF is equal to E of the cathode minus E of the anode. At the cathode, the value is 0.34. So 0.34 minus 2.36. And that gives us a value of 2.7 volts. Question 8.4, state one function of the salt bridge. It is to complete the circuit. It completes the circuit, it completes the cell, it's used for cell neutrality. Any one of those is fine. Question 8.5, how will the following changes affect the initial EMF of the cell? Write only increase, decrease, or remain the same. If they increase the concentration of the Mg2 plus ions, what happens to the EMF? To answer this question, I'm going to write out the overall cell reaction. So we're going to have Mg plus Cu2 plus producing Mg2 plus Cu. Now there are a number of ways that we can get this reaction. I've just used the simple method. You can anyway, so here this, if we imagine it as a reversible reaction, we can apply Le Chatelier's principle. If the concentration of this increases, the reverse reaction is favored. Now there's a simple rule here without going too much into theory, and there's actually an equation that we can use there, but that's beyond our scope. If the reverse reaction is favored, that means the EMF is going to decrease. And if the forward reaction is favored, then the EMF will increase. So the answer here is it is going to decrease. Question 8.5.2, if the area of the copper rod is increased, there's going to be no change. That's not going to affect the forward reaction or the reverse reaction. So here it is going to remain the same. Let's take a look at question number 9. Impure copper is refined using an electrolytic process as shown in the diagram below. Question 9.2. Name a suitable solution that can be used as an electrolyte in this process. Now because they are refining copper, the electrolyte needs to be some copper solution. So one copper solution can be copper sulfate. You could use copper nitrate as well, but copper sulfate is the common one. Question 9.3, write down the equation for the half reaction taking place at the anode. Now at the anode, during the refining of impure copper, that's where you're going to find the impurity, or that's where you're going to find oxidation taking place. So we're going to have copper, so Cu, oxidizing to Cu2 plus 2 electrons. Question 9.4, A precious metal such as silver, which is usually part of the impure anode, sinks to the bottom of the cell. Explain this observation referring to the relative strength of the reducing agents. So let's compare copper and silver. So the reaction for silver is down here, and the reaction for copper is up here. Because copper is higher up, copper is a better reducing agent. That means copper is going to be oxidized. And that's our explanation. So our answer here is going to state that copper is a better reducing agent than silver. Hence, the copper will be oxidized instead of the silver. So if the silver is not being oxidized, it's going to form, or it's going to fall to the bottom instead of the silver. And the last question, question 9.5, after 10 minutes, 1.6 grams of pure copper is deposited on the electrode. Calculate the number of electrons that flowed through the circuit while this mass of copper was deposited. Now I'm going to use the formula M is equal to QM divided by ZF. Now, this is a shortcut. Instead of using the long method to solve it, Q is basically the charge in coulombs. M is the molar mass. Z is the number of electrons transferred during oxidation or reduction. And F is Faraday's constant, 96,500. So we know the mass is 1.6. That's equal to Q, which is what we want, multiplied by the molar mass of copper, 63.5, divided by, when copper is reduced, 2 electrons are used. So 2 multiplied by Faraday's constant, 96,500. Q is then equal to 4,862.99 coulombs. We can now use the formula Q is equal to N times QE, and we can solve for the number of electrons that have flowed. So 4862.99 is equal to N multiplied by 1.6 times 10 to the negative 19. N is then equal to 3.03 times 10 to the 22 electrons. And that's it. Thanks so much for watching.